Hey, welcome to The Explainer. So today we're going to tackle a term you see absolutely everywhere, but maybe don't really know what it means, pH. We're going to break down the science behind this super fundamental concept.
I mean, you've seen these words plastered on everything, right? Shampoo bottles, skincare, even your bottled water. They're just thrown around all the time. But what are they actually telling you? What does it really, truly mean for something to be pH balanced? Well, let's find out.
So to get to the bottom of it all, we've got to start with the most basic question you can ask. What in the world is pH?
All right, so the term itself, which was first coined by a Danish scientist named Sørensen, literally stands for potential of hydrogen. It's basically scientific shorthand for measuring how many hydrogen ions are floating around in any given solution.
But okay, let's just cut through all that science speak for a second. At its very core, pH is just a scorecard. It's a simple way of telling us how acidic or how basic, which is also called alkaline, a substance is. That's it.
So how do we know what's acidic and what's basic? Well, everything is measured against one single benchmark, pure water. Scientifically speaking, pure water is the perfect middle ground. It's not acidic, it's not basic, it is perfectly neutral. And that neutrality, that's our official dividing line.
So here's the bottom line. If a solution has more hydrogen ions than pure water, we call it acidic, and its pH value is going to be less than 7. If it has fewer hydrogen ions, we call it basic or alkaline, and its pH is going to be greater than 7. It's a pretty simple division, right? And to help us visualize all this, scientists came up with a really simple tool. The best way to think of it is as a ruler, but a ruler for acidity, the pH scale. This scale usually runs from 0 all the way to 14. Way down at 0, you've got the most acidic things you can imagine, like battery acid. Then you go all the way up to 14, and you've got the most basic stuff, like drain cleaner. And right there, smack in the middle at 7, that's our neutral point, pure water.
Okay, but listen up, because here's the single most important and often misunderstood thing about this scale. It is not like a regular ruler. The pH scale is logarithmic. What that means is that every single whole number you go up or down is a massive 10 times jump. Let's put that into perspective. Something with a pH of 4 isn't just a little more acidic than something with a pH of 6. No way. The jump from 6 down to 5 is a 10-fold increase in acidity. And the jump from 5 down to 4 is another 10-fold increase. So a pH of 4 is a staggering 100 times more acidic than a pH of 6. That's what makes this scale so incredibly powerful.
Okay, so that's the theory. But why should you care about any of this in the real world? Well, when you get into fields like medicine and pharmacy, controlling pH isn't just some lab exercise. It can literally be a matter of life and death.
You see, a medicine's pH affects pretty much everything about it. We're talking about really basic stuff like, will the drug even dissolve? Will it stay stable on a shelf? Can your body even absorb it properly? It even affects the purity of proteins and how well critical enzymes work. And, on a personal level, it's all about comfort. Getting the pH right is the difference between eye drops that feel soothing and ones that really, really sting. And believe me, the stakes here are incredibly high. As our source material puts it, the wrong pH isn't just uncomfortable. It can cause serious irritation, a burning sensation, or if it's injected, it can even destroy your red blood cells. So yeah, getting the pH right is absolutely non-negotiable. So if keeping a specific pH is so critical, how do scientists stop it from changing? Well, they use these things that are kind of like chemical bodyguards. They're called buffers. So what is a buffer? It's basically a special chemical mixture that has one job, and one job only, to resist changes in pH. You can add a little bit of acid or a little bit of a base, and the buffer just absorbs the shock, holding that pH level almost perfectly steady. A really great way to think about it is like a thermostat for chemistry. A buffer sets the pH at exactly the level you want, and then it just works to keep it there, no matter what. This makes sure the chemical environment stays stable so medicines can do what they're supposed to do, safely and effectively. Okay, so we know what pH is. We know why it matters. We know how to keep it stable, but how do scientists actually, measure it in the lab? Well, there are basically two main ways to do it. First, you've got the colorimetric method. You probably remember this from science class, using those little paper strips that change color. It's cheap, it's easy, but it's not super accurate, and it's useless if your liquid has any color to it. Then you've got the modern way, the electrometric method, which uses a highly accurate digital meter. It's the gold standard. And here it is. This is the modern workhorse, an auto-digital pH meter. That little glass probe you see is an incredibly sensitive electrode. It measures the electrical potential in the liquid, which is directly tied to the hydrogen ion concentration, and it gives you a super precise digital reading. Now, using one of these isn't just a simple dip and read kind of thing. It's a very careful process. First, you have to set the meter to the exact temperature of your liquid. Then you have to calibrate it using standard buffer solutions, usually one that's neutral and then another that's either acidic or basic. This makes sure your reading is dead on accurate. Only then can you rinse the electrode and finally test your solution to get a reliable pH value.
And all of this science, it brings us back to one final fascinating thought. Your own body, especially your blood, is an incredible pH balancing machine. It uses these complex buffer systems to keep your blood at a precise pH of about 7.4. It is an absolute master of this chemical balancing act. So the big question to leave you with is this: what happens to our health when that delicate internal balance fails?